Okay, recorded rolling. Tuesday, January 13th. So we're going to cover angular momentum. So I'm going to cover similar content that I did in my AP classes, just not quite as deep. So keep you guys all on track. I got some posters for you guys, got some demos. Yeah, I'm pretty sure we'll have some time to do some textbook puzzles here. Right. Also have this note, journal school. So next week, Friday, so about a week and a half from now, there's going to be pictures. So senior panoramic. This is Friday the 23rd. The senior panoramic is going to be first period, I think. So if you're a senior, probably get out of first period for some time. They go to the gym, get a panoramic. But also, if you're in any clubs, then figure out what time your club photo would be taken. Because I know how they do this last few years is it's just like, oh, I have a 10 o'clock photo. It's like, hey, 10 o'clock, that would put me like maybe in the middle of second period. So then you have to tell your teacher, oh, I have to go get a club photo. Okay, you have to do that. All right, so some details there. So let's look at angular momentum. Actually, a good place to start this would be with some demos before I jump into the posters and start pulling out equations with you guys. Okay. Hey, guys, this coin right here. Did I ever spin the coin with you guys?
Yes.
Yeah. Right. So see, if I try to balance the coin on its edge, it's really hard. Right. Maybe a nickel is thick enough, but this penny, not really thick. Oh, right. Okay, yep. Thank you. Okay. But see if I give this a spin, right, suddenly all that changes. Right now it does stay upright. Why is it? I see its central axis is spinning around is vertical, right? And what a physicist would say is that angular momentum is conserved. And when I give this a spin, it has this property. It's called angular momentum, right? Okay, and it wants to maintain its orientation, right, and it'll stay upright. Okay? Same thing with this gyroscope here. Now, this gyroscope, if it's not spinning at all, it's just similar thing, right? It's just going to fall over. Okay. There's a little pinhole. Here it is, right here. Okay. And you can push a string through and then wind it around and then pull a string. Make it going really fast, like way faster than the semen. Okay. And if you get going, that's same thing. Or like spinning a top. You guys ever spin a top? Right. So the top, the coin, the gyroscope, they'll all kind of want to balance. And then right when the rotation runs out from frictional forces, eventually it falls over. Right. But why is that? Why would that do that? So let's look at uh, some other examples. The gyroscope here. All right, it's a little slow pace, so you got it muted. Maybe he's just saying the same thing that I was just saying. It's got that. He gives it a spin. Also, as he's turning it like that, it resists changes to its motion. Okay. It's like if you hold it in your hand. Okay. Oh, you can balance this way. Okay. And notice it also processes around. He didn't give it a push or anything. Like, he put it on that angle and just let it go, and it's automatically going around, I guess, clockwise from the top. Okay. Ooh, you can balance it on a string. Okay. Of course, just as long as it's spinning, you can do all these fun things with it. Okay. So a little bit more. Um, right. So why would that work? Okay. Did I recommend to you guys this Vsauce video called Spinning? Right, where he talks about gyros. Well, he talks about a lot of physics of things spinning, right? But there's a couple parts that I want to point out here. Right? So I think I've thrown this link on Google Classroom once or twice in the past this year. And so I do recommend you guys go watch this. But here, let's watch this part right here.
Its velocity doesn't just disappear.
Right. Okay. Rewind a little bit. Here we go. Right, so he's going to roll that ball towards the right, right, and watch, and then he's going to bump it with this cardboard down here. So watch what happens.
Before I touch it, its velocity doesn't just disappear. Instead, both combine and the ball moves according to their sum. The lower its initial momentum, the greater this angle. Now, let's go back to circular motion. Imagine a satellite orbiting Earth. Its velocity is, as we showed before, at all times tangent to its circular path. A centripetal force from gravity continuously swings its velocity around so that every 90 degrees it starts pointing more and more in the opposite direction it used to be. Just like with the ball, a downwards force won't send it straight down. Instead, the vectors combine, resulting in a new path like this. 90 degrees ahead, it reaches the maximum distance it will travel in the direction of our force before going back. The key point here is that a downwards force at this location didn't move the orbit like this. It moved the orbit like this, tilting it 90 degrees ahead of where we acted. Now, imagine the satellite as a small piece of our gyroscope. Pushing down here will cause the piece to assume a path that would take it like this. But of course, since the disk is solid and all of its pieces quite rigidly push and pull each other, the gyroscope itself tilts like this.
Yeah, and that's the key. That's why the gyroscope doesn't fall over while it's spinning, or the coin for that matter, or anything, or a top if you spin a top. Right? Because whichever way it's leaning, you say, okay, well, there's its weight is going to cause sort of a net force in that direction. Right? Right? But because it's spinning, it actually wants to fall 90 degrees ahead of its motion. Right? Hence, it'll actually process around rather than falling down. There's actually one more part I want to show you in this video. I'm going to zoom ahead a few minutes. Right? Bicycle wheel. Right, but went too far.
In the rotation, so the wheel will turn like this, but well, there's still a torque here pushing the bottom of the wheel this way, moving that 90 degrees ahead. We see that the wheel will just keep turning, and in fact, that's what it will do. If I can get it up to a fast enough speed, then ta-da!
See, it looks like it's sort of levitating there, but it's also processing around at the same time. Okay. Here, I'm gonna do that one live in class. Okay, so, of course, I'm doing a video recording now. If you watch this video, then kind of have to miss this one out. But I do have a bike wheel here. Right, it has this axle. Actually, I think you guys in class, you guys had your hands on this the other day, didn't you? Right. So, yeah, had a live type demo. So, you'll have to use your imagination on this one. So here, again, this is spin, but it's really the same thing as the Vsauce video you just saw. Right? Now, but before I spin this, if I try to balance this on this endpoint, well, that makes no sense. It's just going to fall straight down. Right? But if I give this a spin, it's going to look like it's levitating. Right there. Yeah, you guys see that? Okay. Notice it's also processing around. Okay. Now it's leaning a little bit way, so it's processing one way. But what if I pull it the other way? Now if I grab it on the other side, it processes the other way. Okay. Right. Also, I noticed that here, if I try to turn this like 90 degrees, I definitely feel a resistance to change in motion. Maybe you guys can feel this at the end of the class too, right? It doesn't want to change its orientation, right? Like the top wanted to stay upright or gyroscope or not. Right here, I got a turntable here. So what if I also stand on the turntable at the same time I try to turn this? Guess what's gonna happen? Find out. Whoa, whoa, yeah, the whole turntable beneath the turns. Oh, yeah. All right. And so, yeah, so complex motion there, but it goes to conservation of angular momentum. We got it. All right. Where did? Okay, here we go. All right, so we're gonna go through the same set of posters with you guys as I did for my AP, so that I know I've covered these with you guys. I just won't go quite as deep. Okay. So all right. Back to if you guys like, I might go ahead and upload the AP video too, just so you guys can see more complex version of this. Okay. But one classic set of questions involves: what if I take that turntable you guys just saw here? Got it. You can throw this in front of the camera. Okay. What if I take this turntable right here and I wrap a string around it and I pull the string? Okay, get it to spin. So that's what this is showing right here. So here's the tension of the string, respect force, and maybe the string is wound around. Okay. Now, conveniently for the setup, no matter how I pull the string, this string tension is always perpendicular to this radial arm. So the torque I get out of that, you guys remember torque, R cross F? This R cross this F, this is always a 90-degree angle. Okay, so I always get the maximum possible torque. Okay, so that's nice. Okay, so I'm pulling. Now, suppose here's a little simplification, but this is a common simplification. Suppose there's no friction with the axle. Guess that this dashed line could be like a central axle here. Okay, let's get rid of that friction. Well, whatever torque I apply, R cross F, that's going to result in this speeding up spinning. It's called angular acceleration. It results in I times alpha, because that's the other perspective on torque, isn't it? You guys remember Newton's second law of motion, F equals ma? This is the rotational form. Torque equals I times alpha. Yeah. Okay. So R cross F results in I times alpha. No, what is this I right here? That is this rotational inertia. And guys, this turntable, isn't it basically this? Right? This solid cylinder, right? If I just turn this up right, yeah, I mean, it's real flat, but that's a shape. It's a solid cylinder like that, rotating about its center. Okay, so 1/2 m squared. So if I knew the mass of that top surface and I knew its radius, let's do that real fast. That might be a good idea. Okay. I'm gonna make a guess. Here, I kind of hold these like Indiana Jones, Raiders of the Lost Ark. Okay, that feels kind of right, something like that. Maybe these feel kind of similar. No, put them on a scale. But you guys get the idea. See if this is half a kilogram. This feels kind of similar, but it's like two plates put together. I'm gonna estimate here. I'm gonna call this top plate that's spinning right here. Let's call this 0.2 kilograms. I don't know. It might be pretty close to that. That's it. Now let's get a radius on this thing. So this radius right here. Right. Now this is an octagon, but it's pretty close to a circle. It looks like this radius is about 15 centimeters. Yeah, 15, 16, somewhere there. 15. Okay. So let's take those two values, put them together to get a rotational inertia for that turntable. Okay. So if I say the rotational inertia of the turntable is approximately, okay, so 1/2 mr squared, 1/2, I'm going to call the mass about 0.2 kilograms. And that radius is about, okay, 15 centimeters, kind of 0.15 meters. Okay, and that's being squared. Okay, this is a real rough calculation, but it might give me a pretty close idea. 0.5 m r squared. Okay. Now, do you guys remember when the last lab that we did in class together? Remember the rotational inertia lab? That whole big pipe system? The rotational inertia was roughly like 0.1 or somewhere in there, kilogram meter squared. So what is this? Yeah, so we're talking about really small decimal values. So roughly 0.002 something. This would be kilogram meter squared. Okay. So that tells you how much resistance to change in motion does this have. This is how you can quantify that. Okay. All right. So what next? All right. So back to here then. Okay. If I'm back to my string wrapped around it and I'm pulling, okay, that's going to cause it to speed up spinning. And how much does it speed up spinning? That's this angular acceleration. Well, it depends on its rotational inertia. So the more inertia it has, the more difficult it is to get it to accelerate. Right? Something like that. Right. Also, while I'm pulling with a constant tension, giving it some torque, isn't it, guys? Isn't it actually speeding up faster, faster, faster? Ooh, hence the acceleration right here. Okay. Now, what you guys saw with maybe I should have shown you this first, right? With the top and whatnot. You guys remember that conservation of angular momentum, say with the gyroscope? And so what is angular momentum? Right. So in physics, that's capital L, right? And it's I times omega. So you guys remember regular linear momentum was mass times velocity? You guys remember that? Right. Well, if you translate it over to rotational motion, what's going to take the place of mass is rotational inertia. What takes place of linear velocity v is this angular velocity omega. Okay, so this is a type of momentum. It's just angular, and that's going to be conserved. I think Winter Olympics are coming up pretty soon, right? So when you guys watch figure skaters, you guys seen a figure skater go into a slow spin and they pull their arms in? And guys, what happens when they pull their arms in while they're spinning?
Oh, they get faster.
Get faster? Did I show you guys the Paul Hewitt on this?
Should decrease
Somebody send Here.
velocity.
Here, got it.
It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotation inertia or a little? How about when I pull them in? A little? So if I get here rotating like this and I hold them out, what happens when I pull them in? Ooh, easier to rotate, gang. Harder to rotate. Easier to rotate. Okay. You see such thing? All right.
Wrong one. That's the wrong window here. Okay, there you go. Right, so this is what you guys just saw. Okay. So the principle here is conservation of angular momentum. That's been the theme all day today. Okay. Okay. So I times omega. Well, when you pull your arms in like that, you are decreasing your rotational inertia because your mass is getting closer to your axis of rotation. Wasn't that true for, if we go back to this table? Right. You guys see the common theme here? Like if I compare this ring to the solid cylinder, the ring, the mass is distributed far away from the axis of rotation. The solid cylinder, the mass is distributed closer in. Suppose these were like equal mass, right? You put them on the scale, they weigh the same sort of thing, and equal radius. Right? Well, they would have different rotational inertia, right? Because this ring out here, right, the mass is distributed very far away. A lot of them are squared. The solid cylinder, a lot of it's closer in, so the net effect is half. Okay. Right? So yeah, so you're decreasing rotational inertia, right? But angular momentum is conserved, right? Therefore, your angular velocity has to increase. Right? So there's like an equation explanation for why you would speed up spinning, or the figure skater would speed up spinning like that. Okay. How about this? Guys, to go from this picture on the left to the picture on the right, suppose you're the figure skater. Do you have to pull your arms in? Does that take some effort? Right? And in physics, that would be called work, right? Okay. Work. That's like a transfer of energy. So, suppose you now we haven't even talked about kinetic energy of rotation quite yet, but I think you can figure this out if you think about this. Here. Suppose you calculated the rotational kinetic energy in the picture on the left, where figure skaters spin around real slow, and the rotational kinetic energy on the right is spin around real fast. Okay. The formula, by the way, ends up being 1/2 I omega squared. So it's like the same ingredients here, we just do different things. Okay. Which one of these do you think would have more rotational kinetic energy, left or right? How many of you guys think the one on the right? Yeah, right. And there would be this competing effect because less I, more omegas. Okay, well, which one's which? Okay. But when you run on 1/2 I omega squared, you will get more on the right. You can quantify that. Okay. And where the energy comes from is from the figure skaters' muscles as they're like pulling their arms in. Okay. That takes work. So you're transferring energy from your muscles into your motion. Okay. So you get that. All right. Okay. So here I'm really trying to build this up. Okay. So still got to finish this story though. Okay, so I got my string wrapped around this turntable. I'm pulling, right, speeding up, spinning. Right? So, guys, what's happening to this angular momentum while it's speeding up spinning? Is this like as time passes? Right. So the I is constant, but what's happening to this omega? Is it spinning faster, faster, faster? So this is going up, 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 up. Right. So I'm giving more and more and more angular momentum to that turntable. Do you guys see that? Okay. Right. So here, show you guys please. All right, if you made a couple of graphs side by side, they're looking at different properties of that turntable while you're speeding up spinning. Suppose I was plugging a constant torque, and then the number of seconds got times 0, 1, 2, 3 seconds. Okay. But a constant torque that could look like that, just flat line. Okay. But it would be speeding up spinning, so its angular momentum would be increasing. Okay. And these two graphs are related. So like if I covered up one of these and you only had the other graph, you could figure out what the other graph kind of looks like. Right? There's a calculus type connection here, right? So the accumulated area under the curve, torque versus time, right, tells you the change in angular momentum, right? And then go from right to left, right? The rate change of angular momentum, which is the slope of this graph, tells you the torque. And since I have a constant slope on the right side, I have a constant value on the left side. Like I said. All right, so a little detail there. All right, let's keep going. Ooh, this next one's fun. Here, do this with you guys. All right, spinning a basketball. Right? So picking up from that last pair of graphs right here. Right? Remember, if I apply some torque for some time interval, do you see a nice green rectangle right here? That's the change in angular momentum. Right, you guys see that? Right. So that's about to be really helpful with spinning the basketball. I'm supposed to have a basketball in my finger and pow, get a little kick right here and start spinning. How fast is it spinning? Ooh, right. You guys ready to figure this out? Okay. We're going to do some terms of variables. I'm just going to uncover step by step. And the last step says omega equals something. So how fast is it spinning? Right, you guys got that? It's like if I kick it like 3 times the force, is it going to spin a lot faster? Do you think it'd be at 3 times as fast, maybe? Or maybe, probably. Right? We'll find out. So the starting line comes from that last page, right? That big old green rectangle. Right? That's the same thing as this green rectangle right here. Right? Torque times time tells you the change in angular momentum. Right? Let's say the basketball starts at rest. Pow, give it a little kick. Right, so let's go through step by step. Because I can know the radius of the basketball. Maybe I know the mass of the basketball. I can figure out its rotational inertia. So more on that later. Right? And maybe how hard I hit it. And maybe the time I hit it for. Like pow, maybe a tiny fraction of a second, maybe at 0.2 seconds or something. Right? Can you guys imagine all that? Right? So let's put this together to figure out how fast it's spinning. Right? So series of substitutions. I need to substitute something for this torque. Right? No, because we've been talking about torque for over a week now. So what is torque equal to? What times what? Yeah, this is R cross this F. Okay. And conveniently, these will probably be at 90 degrees to each other anyway. So can I just replace that torque very simply with right, R cross F? That takes the place of that torque. Right? And then delta T, that's the time interval I apply the force for. How about angular momentum? Let's see. Okay. That goes back to here. You guys remember angular momentum is I times omega? Okay. So no, as long as the basketball starts from rest, then the change in angular momentum is the final angular momentum. So I can just call it I omega. All right, what next here? Ooh, guys, how about the fact that I have a basketball specifically, right? That tells you something about how the mass is distributed. Okay? Like here, if I had a solid foam ball next to a basketball, let's say I have the same mass and the same radius, but one's solid foam and one's a well, guys, a basketball isn't all the mass pretty much on the surface of a sphere,
Yeah.
and maybe there's some air inside, but that doesn't really do very much towards mass. Okay. So that tells me how the mass is distributed. That's something to do with this right here. You see that? Tells you how much inertia it had, right? Versus if it was a solid foam ball, wouldn't it be more like this one where it was solid all the way through? Right. Okay, so then that would actually spin differently. Wonder which ones maybe spin faster. You can answer that too. Okay. So do a little comparison. Okay. But what I'm trying to build up towards is I'm about to substitute out which variable in this line.
That's
Yeah, this rotational inertia right here. Okay. This is a basketball, I'll call it 2/3 MR squared. Right. Okay, so now I know that. Okay. And I could reasonably know the mass of the basketball, and the radius of the basketball. So boom, boom, got that. Okay. I can know what force I apply, like pow, and how much time. Right? Maybe I apply like 50 newtons of force for like 0.2 seconds. Right? Those could be numbers I could reasonably attain. Okay? So all we need to do to get how fast is the basketball going to spin is a little bit of algebra. Okay? Because which variable, can you guys see some algebra? Which variable partially cancels out? Yeah, R. So R on the left side, and well, this R squared just becomes R to the 1. So still gonna get an R in the equation. I do.
You did it early, so.
Ah,
papers come in.
yeah, thank you.
Or do you want me to put it in?
Right, yeah, right, here. Okay, so anyway, you finish the algebra, it's gonna end up looking like that. Right. All right. Yeah, if you just pick that down, yeah, it'll all set up. So all right, yeah, thanks so much. All right. So here, let's read the music of this equation, see if it kind of makes sense. Is what if I had this basketball and I kick it with 3 times the force, or like instead of just the force, pow? What if I do like a really hard force, pow, like 3 times the force? Is it going to spin faster?
Yeah.
How many times faster? 3 times. Yeah, a factor of 3 on the Zeph is going to be 3 times the omega. Okay. What if I hit it 3 times, like pow, pow, pow? Isn't that sort of like tripling the amount of time that I apply the force for?
Yeah.
Right. And is that going to make it spin how many times as fast? Also 3 times, right? But like if you hit it 3 times, it's going to spin 3 times faster. Okay. Guys, what if I replaced the surface of the basketball, like whatever basketball material, with like lead? Make like this big lead ball. It's really massive. Hard to hold my finger. Is it going to spin faster or slower?
Slower.
Yeah, slower because it has so much more mass, like more inertia, isn't it? Right. Okay. And then this 3/2 I left in orange because it applies to the basketball. But what if I replace this with a foam ball, which is more like solid? Okay, so this would be 2/5. That would go right there. What would this be? Yeah, it would be 5/2, wouldn't it? So okay, suppose you have a foam ball next to a basketball, and all else equal. Okay, same mass, same radius, same kicking force, the whole deal. Okay. But one's solid, and then this basketball, of course, is hollow. Okay. Which would actually spin faster, the foam ball that was solid, or the basketball that's more like a shell? Which spins faster? Okay, so show hands. Show hands. How many of you think the foam ball spins faster? How many of you say the basketball spins faster? I'm gonna go with the foam ball.
Yeah.
The foam ball, right? Because its mass is more distributed closer in, right? Which all else equal gives it less rotational inertia, right? 2/5 is like 0.4. 2/3 is like 0.67. Ooh. So, or if you like, it's going to translate to the end as 5/2, right? That's another way to think of it. Right? So I think the foam ball actually spins faster. Okay. Right. These discs are fun. Again, like if you were to take AP, and this is a question that comes up all the time. Right? Guys, could you imagine if I have a turntable here that's great? You guys see this green turntable? And what if I have a separate gold turntable and I slowly lower it onto that green turntable? Right? And they stick together. Right? Isn't however fast the green one was spinning, isn't it going to kind of slow down a little bit? And this gold one, which maybe used to not be spinning at all, now it's going to pick up, right? Something like that. Right? And now, in terms of angular momentum, if I make an angular momentum versus time graph, right? Here was say like the gold one wasn't spinning at all. That's this curve right here, and the green one was spinning. Okay, right? And then they stick together. Okay, and then this red line represents the angular momentum of the 2-disc system, which is conserved. I mean, the whole guiding principle here is conservation of angular momentum. Okay, okay, so whatever's lost by the green is exactly picked up by the gold. Okay, and there's different ways this could play out, but that's one. Okay. This one's kind of fun too. What if you have like the swivel stick and you throw a blob of clay at it? That glides here and it gets the whole thing spinning. Okay. How fast does this end up spinning? And one part of the process is that this point mass of clay that's moving in a straight line like a point mass actually has angular momentum, which is kind of a weird concept. It goes like this. When it collides, say, at 90 degrees, it provides a torque, right? So you can take a cross product of where did it land, right? And is my mouse, what's my mouse doing there? Get that out of the way. Okay. Right. Take a cross product of this radial distance from this pivot point and the actual linear momentum of this blob of clay. Right? It can tell you something about the angular momentum of the system. Right? And I'll show you guys a little bit of math here. Right? So again, I just did this with AP, but I'll just do a real fast version with you guys. Right? What if I have a paddle wheel, right? And at this radial distance, I got this blob of clay that comes in. And how fast does it get the paddle wheel spinning? Right? Right, so I do R cross MV from the clay, and if I gave you the mass and throwing speed of the clay and give you this radial arm, right, I can calculate the angular momentum. I can get a numerical value. Right, right. Then I say, no, here's where it depends: does the clay stick or bounce? I mean, if it's clay, it probably sticks. Right. I say, I know angular momentum is I times omega, so here's the rotational inertia of the wheel, which might be some given value. Maybe I just give you that value. Right, and then the clay is like mr squared. Right, and then here's the angular momentum that was in the system, came off from the clay, right? So you can solve for omega, and you can figure out how fast does the wheel spin. Okay, right, so let's bring that there. Right, so that's fun. All right, let's do at least a couple of puzzles here. Right. Yeah, here. How about this, guys? Let's do 2 puzzles, and then if we have some spare time, I'll just play that Vsauce video. I think that'll be a good way to do class. So let's definitely do number 88 because that's yeah, like an honors level textbook. There might be like a question related to here. Number 88. I think is kind of relevant to what we're doing here. We got a gymnast performing a routine on this bar. First, she does giant swing from the high bar, holding her body straight and pivoting around her hands. Then she lets go of the high bar and grabs her knees in this tuck position. Probably spinning around. Okay. Finally, she straightens up and lands on her feet. How? And the second and final parts of the gymnast routine, what axis is she spinning about? Rank in order from greatest to least the moments of inertia in those 3 positions. And then rank order, greatest to least the angular velocities of those 3 positions. Yeah.
We haven't finished 95 overall.
Oh, did we not?
What were you did?
Oh, I showed you guys how to set it up and think about it. So yeah, did you have a question about that though?
No.
No. Okay. Okay. So yeah, remember. Okay. Here, I can go talk about it a little bit if you want to see it again.
What was the answer to B equals W times M?
Um.
The answer. That's how you set it up.
Yeah, that was like how to frame the question and think about it. So like if you want to see it spelled out, right here, I'll go back to 95. So maybe you got a car with regular wheels. You got a car with like big monster wheels, right? Something like that. Right. So you replace the regular wheels on your car with these monster wheels. Right? And with the regular car, if the wheels make one rotation, then maybe the cars move this far. Okay. And then your car's like an internal clockwork and says, oh, okay, well, if I went this far X, which is the circumference of the wheel, in so much time, I can tell you how fast you're going. You're going 45 miles an hour. Okay. But if you put on the monster wheels and this wheel makes one rotation, it's gone much, much, much further. Okay? In fact, guys, if it's twice the radius, does it also have twice the circumference?
Yeah.
And wouldn't this actually be more like 2x? If this radius is r, and this radius is like 2r, I'm just making something up. Right? Right. And then no, your car thinks, oh, okay, I did one wheel rotation in so much time, it must be going 45 miles an hour. But you've actually gone twice as far as the car thinks you went because the tires are way too big. Right? What that means is, guys, you're not going 45 miles an hour. You're going how fast?
Or 90.
90 miles an hour. Your dashboard says 45, but the cop with the radar gun says, here's your radar gun right here. Says, no, you're going 90 miles an hour. Okay?
Does that mean the cars with bigger wheels naturally go faster on the highway?
Well, okay, yeah, actually, that's a really good question too. Right, guys, if you put on really big tires or really big wheels on your bicycle or something, right, does that make you go faster in general? And the tricky answer is actually no.
Doesn't it cause or take more force to spin it? All that.
Yeah. Right. Because right, the bigger wheel, yeah, it'd be harder to get it go. Right, so there's sort of a cancellation effect, and actually a better way to to frame it is not in terms of torque or angular velocity or anything like that. It's actually in terms of energy, right?
Yeah.
So like it here for both of these cars to move some distance, it might take a similar amount of gasoline, right? So you're not really getting more fuel efficiency by having like monster wheels on your car, right? Even though intuitively it seems like it seems like you could, but they don't really work so well that way. Right? Same thing like pedaling your bike. You put on like big old bike tires, right? It takes more effort, like more force from your legs to like paddle the bicycle, right? And so to go like 1 mile is a similar amount of energy from yourself, right? So you end up not really going any faster, right? But all right, thanks so much. That's awesome. Okay, so what was the actual question here? How will increase in the diameter of the tires affect the reading of the speedometer? Okay. So increasing the diameter of the tires. All right, thanks. Will cause the speedometer to the speed of the car. Guys, what goes in this blank? Overestimate or underestimate?
Over.
Wait a minute. The clock knows you're going 90 miles an hour.
Yeah.
You think you're going 45. Yeah, underestimate. Underestimate.
You should.
Okay. From that whole process we talked about yesterday. Okay. Okay, so that might be a good way to write the answer. Okay. All right. Yeah, let's do 88, and then I'll roll up Vsauce. Okay, so 88 right here. So we got this gymnast doing these flips. Now, yeah, I'm gonna look at this. I think the answer to this kind of depends on how you interpret this in a way, well, especially for that last position. And so, part A, this is 88A, right, says what axis is she rotating about? Well, here we're going from this picture on the bar here, right, spinning about the bar, of course, right, spinning about the bar, okay, to now she's in this tuck position. So draw somebody kind of in tuck position here, spinning about her own center of mass, right? Spinning about, okay, and then she goes and lands on the floor. It's like terrible looking stick figures. Okay, hey guys, when she's landing on the floor, now if she's like 1 millimeter above the floor and she hasn't hit the floor yet, she is still rotating about her own center of mass. Mm-hmm. But when her feet land on the floor and there's friction with the floor, I think
She's rotating the ball.
yeah, she'd be rotating about her feet, wouldn't she? Right. So, how do you guys want to interpret that going forward? What do you want to say is her axis of rotation for the last frame?
When her feet hit the ground, she's
Yeah.
now rotating down.
Rotating. Which axis do you guys want to go with?
Ground.
About the ground or her feet?
Yeah.
Yeah. Okay. Let's go with that one. Right. Yeah, it's kind of interpretation. Okay. So, question A says, right, here, I'll call these frames A, B, and C. Right. So in frame A, axis of rotation. So axis of rotation is right. I would call this the bar, right, up here, and then frame B, it would be her own center of mass. Okay. And then when we get to frame C, yeah, let's call it her feet. Her feet, right? And it looks like the first frame and the last frame are fairly comparable, right? In terms of rotational inertia, because they both make me think kind of like this one right here, something about like 1/3 ml squared. If you know her mass and her height, be probably pretty able to estimate by that. Okay. Maybe a tiny bit more in frame A because she's extending her arms a bit. Okay. But then, do you guys think in frame B she has the smallest rotational inertia because she's in that tuck position, she's rotating about her own center of mass? Okay. Okay, so that should be the smallest rotational inertia. Was that the next question? Question B is breaking order. Her moments of inertia. So I'll have I sub A, I sub B, and I sub C. It says rank greatest to least. So let me have these type inequalities. So something greater than something greater than something. but I need some subscripts. Right. So I think I accidentally just gave this away, but let's see if you can either figure this out or if you were listening, one or the other. Right. Guys, which of these three frames does she have the greatest rotational inertia?
The second one. No. Or it's the, no, it's the first.
Yeah, I think the first one would beat this last frame by a little bit, right? Because first one she has her arms extended, right? And the last one she's standing on her feet. So both of those are probably fairly similar to this picture right here. If you stand this upright, something like this, right? 1/3 ml squared. But I think she's like extended a little bit in picture 8 compared to C. So I'm gonna say A is a little bit bigger than C. And then B, where she's in this tuck position and flying around, I think that would be definitely the smallest rotational inertia, wouldn't it? Okay. All right. And then question C was rank her angular velocities. Right. Well, from frame A to frame B, I think angular momentum would be conserved. Right. So A and B you can definitely compare. Because where she's spinning faster, A or B?
B.
Definitely B. So omega B is definitely faster than omega A. Right. Now here's where things get kind of tricky is frame C. Now if she was like 1 millimeter above the ground, then I would say angular momentum is still conserved within herself. Like that would be a closed system. As soon as she lands on the ground, now she's connecting with the ground and maybe causing the Earth to spin slightly differently. Right? But her own angular speed, guys, is she really spinning anymore at point C? No. So I would say omega C is equal to 0 radians per second. Right? And that's if you do this interpretation of she's rotating about the floor and it just comes to a stop. Okay. Although that one's, change the system a little bit for that to happen. Okay. Hey, you guys see that? Okay, so with that set of interpretations, I think that would be a good set of answers. Okay. All right. So pretty good. Pretty good. I think we're doing. Yeah, I'm gonna close down this recording and play Vsauce for you guys.